That little blue dot on your phone. It's a miracle. Not a figure of speech, a genuine, technological miracle. And it's only possible because of a ghost, the ghost of Albert Einstein. Because without his century-old, brain-bending theories on how time itself can bend, stretch, and break, your phone wouldn't just be a little off. It would be lost by miles within minutes. Your morning commute would end in a different city. Today, we're going to pull back the curtain on the single greatest magic trick in modern life. We're going to find the ghost in the machine. And reveal how your phone performs this daily act of wizardry, by listening to a choir of atomic clocks singing a song written by the master himself, Albert Einstein. So, how does it all actually work? To start, you need to forget everything you think you know about finding your location. Forget paper maps, forget star charts, forget sextants. The global positioning system is not, at its core, a system for finding where you are. It is a breathtakingly precise system for finding out when you are. And it has to know when with a level of precision that is almost impossible for a human brain to truly feel or comprehend. To understand this, let's start with an analogy you can feel. Imagine you're standing at the edge of a truly massive canyon. It's foggy, you can't see the other side. You want to know how far away it is. So you do something simple. You cup your hands and you shout hello into the mist. Then you wait. You listen. A few seconds later, you hear the faint echo of your own voice come back. You pull out a simple stopwatch. You clicked it the moment you shouted, and you clicked it again the moment you heard the echo. Let's say it took exactly 4 seconds. Now, if you know the speed of sound, which is roughly 343 meters per second, you can do some simple math. The sound took 4 seconds for a round trip, so it took 2 seconds to get there. 2 seconds times 343 meters per second. The other side of the canyon is about 686 meters away. Simple. This fundamental idea is called a time-of-flight system. You measure the time it takes for a signal to fly from a source to a receiver, and if you know the speed, you know the distance. Now, let's scale that up. Way up. Orbiting about 20,000 kilometers above our heads is an incredible constellation of machinery. It's a network of around 31 active GPS satellites, moving at immense speed. They're arranged in 6 different orbital planes, a carefully designed celestial web that ensures that from almost any point on Earth, at any time of day, you can see at least 4 of them. And just like you at the edge of the canyon, each one of these satellites is constantly shouting a very simple message down to us. It isn't a voice, of course, it's a complex radio signal. But the core of the message is basically this: hello. My serial number is 27. The time is now. And I am right here. Your phone is the listener in this cosmic canyon. Its antenna is constantly scanning the sky, listening for these faint whispers from space. It catches these signals from multiple satellites at the same time. And just like you and your stopwatch, it measures the time of flight, the incredibly short time it took for each signal to travel from the satellite to your hand. Since these signals are radio waves, they travel at the speed of light, a universal, unchanging constant, the ultimate speed limit of the cosmos. So your phone's tiny processor does the math. Distance equals the speed of light, multiplied by the travel time. Now the geometry kicks in. If your phone hears a signal from one satellite, it can calculate its distance from it. Let's say it's 22,000 kilometers from satellite A. That means you're not in one specific spot, you're somewhere on the surface of a giant, imaginary sphere with that satellite at its exact center, and a radius of 22,000 kilometers. That's helpful, but you're still basically lost. So your phone listens for another one. It hears from satellite B, and calculates it's 23,500 kilometers from that one. Now you have 2 giant spheres, and they intersect. The place where they meet isn't a sphere anymore, it's a perfect circle. You've narrowed your position down from the entire surface of a sphere to a single massive ring in space. Getting warmer. Then, a third satellite chimes in. Satellite C. Its sphere of position slices through that circle, and the intersection of 3 spheres gives you just 2 possible points. One of them is usually a ridiculous location, like deep inside the Earth or flying in the upper atmosphere, so it's easy to discard. You've found yourself. This beautiful geometric trick is called trilateration. It's simple, it's elegant, and it seems utterly foolproof. But there's a massive, civilization-sized catch hiding in that one simple word: time. This whole elegant system, this celestial web of intersecting spheres, depends entirely on one single, critical thing: a perfect stopwatch. Let's go back to our canyon. If your timing is off by a whole second when you're measuring the speed of sound, your distance calculation is wrong by a few hundred meters. A big error, but maybe not a disaster. But when you're measuring the speed of light, the stakes are astronomically higher. Light travels at about 300,000 kilometers, or 186,000 miles, per second. So if your stopwatch is off by just 1 second, your calculated position is off by 300,000 kilometers. You're not just in the wrong city, you're beyond the orbit of the moon. To find your location with the kind of accuracy we expect, down to a few feet, the timing has to be perfect. The entire GPS system needs to measure time down to the nanosecond. A billionth of a second. Let's try to wrap our heads around that. A nanosecond is to 1 second what 1 second is to nearly 32 years. Light itself, the fastest thing in the universe, travels only about 30 centimeters, less than 1 foot, in a single nanosecond. That is the razor's edge of precision GPS lives on. An error of just a few nanoseconds can mean the difference between your car being in the right lane, or in the ditch. And here's the devastating problem: your phone is a terrible clock. Inside your phone, and in most consumer electronics, the thing that keeps time is a tiny, vibrating shard of quartz crystal. When you pass an electric current through it, it oscillates at a very specific frequency. It's an amazing bit of technology for how cheap and small it is. But it's fundamentally unstable. It's like a cheap guitar string. It plays the right note, more or less, but its pitch changes with temperature, with age, with physical jostling. It drifts. A lot. If you took your phone, fully charged it, then disconnected it from every network, no cell, no Wi-Fi, no Bluetooth, and left it on a table for 24 hours, its internal clock could drift by several seconds. That's not a few nanoseconds. That's a few billion nanoseconds. From a GPS perspective, your phone's clock isn't just a broken stopwatch, it's a sundial in a hurricane. It's completely, hopelessly useless for timing signals from space. So, if your phone's clock is junk, how does it ever get the right time? It borrows it. From the sky. And in doing so, it performs a trick that ties the whole system together. But what makes the clocks in the sky so special they can lend time to the entire planet? And what does any of this have to do with a 100-year-old theory from a wild-haired genius that claimed time itself isn't constant? The answer will fundamentally change the way you think about time itself. Each GPS satellite is carrying something extraordinary. It's carrying a clock. But not just any clock. They carry atomic clocks. These are, without exaggeration, the most precise timekeeping devices humanity has ever conceived of and built. They aren't like a ticking grandfather clock, which relies on a swinging pendulum. They aren't like a quartz watch, which relies on a vibrating crystal. They are more like nature's own metronome, a heartbeat built into the very fabric of reality. To understand them, you have to think small. Incredibly small. Inside these clocks are atoms, usually of an element called cesium, or sometimes rubidium. Like all atoms, a cesium atom has electrons orbiting its nucleus. And these electrons can only exist in specific, defined energy levels, like rungs on a ladder. They can jump up to a higher rung if they absorb energy, and they fall down to a lower rung by releasing energy. Now, here's the magic part. The energy difference between two specific rungs in a cesium atom is incredibly precise and unchanging. To make an electron jump between these two states, you have to hit it with a microwave of a very, very specific frequency. It's like a lock and a key. Too high, nothing happens. Too low, nothing happens. But if the frequency is perfect, the atom absorbs the energy and the electron jumps. That perfect frequency is 9,192,631,770 cycles per second. That number isn't random. Since 1967, that number has been the official, international definition of what a second is. We didn't invent the second, we discovered it, humming away inside the cesium atom. An atomic clock harnesses this fundamental property of the universe. It generates a microwave signal from a quartz oscillator and feeds it to the cesium atoms. A detector measures how many atoms are making the energy jump. The clock then adjusts the microwave frequency until the number of jumping atoms is maximized. At that peak, the clock knows its microwave signal is perfectly tuned to nature's own frequency. It's a feedback loop that enslaves the imperfect quartz crystal to the perfect rhythm of the atom. A quartz clock is like a musician playing by ear. An atomic clock is a musician whose sheet music is written into the laws of physics. So, these satellites are soaring through space, each one carrying a clock that is accurate to within a few billionths of a second per day. And each one is broadcasting its signal that says, according to my near-perfect atomic clock, the time is this. Your phone, with its terrible, drifting quartz clock, listens to at least 4 of these ultra-precise signals. And now, it performs that brilliant piece of logic we mentioned. It says, okay, I know my own clock is wrong. I don't know by how much, but I know it's consistently wrong. I'll call that unknown error my clock bias. by listening to a fourth satellite, it adds a fourth piece of information to its calculation. It's now solving a system of 4 equations with 4 unknowns. The 4 unknowns are your 3 dimensions in space, latitude, longitude, altitude, and the 1 dimension in time, its own clock bias. The processor in your phone runs the algebra in a flash, and it solves for everything simultaneously. It calculates your precise position, and as a side effect, it discovers its own timing error and corrects itself, syncing your phone's clock to the atomic heartbeat of the entire GPS constellation. Problem solved. Absolutely bulletproof. We have perfect clocks. We have simple geometry. Your blue dot should be perfect. Except, it wouldn't be. It would still be catastrophically wrong. Because of Einstein. Here is where the story pivots from a marvel of engineering to a mind-bending journey into the nature of reality itself. In the early 20th century, Albert Einstein, working with nothing more than a pen, paper, and his legendary thought experiments, completely demolished our comfortable, everyday understanding of space and time. He proved they are not the separate, rigid, and absolute background stage we imagine them to be. They are a single, unified, dynamic fabric, space-time, and it can be warped, bent, stretched, and squeezed by motion and gravity. For decades, these were bizarre, esoteric theories. But the GPS satellites, flying high above us, are living, irrefutable proof that he was right. First, there's special relativity. Einstein published this in his miracle year of 1905. The theory is built on a simple, but reality-shattering, postulate: the speed of light in a vacuum is the same for all observers, no matter how fast they are moving. From this one idea, all sorts of strange consequences fall out. One of the most famous is called time dilation. It says that the faster you move through space, the slower you move through time relative to a stationary observer. It's often explained with the twin paradox. Imagine 2 identical twins. One stays on Earth, while the other gets in a super-fast rocket and flies to a distant star and back. When the spacefaring twin returns, they will have aged less than the twin who stayed home. For them, time literally ticked by at a slower rate. Now, GPS satellites aren't traveling at the speed of light. But they are moving fast. They are whipping around the Earth at about 3.9 kilometers per second. That's nearly 9,000 miles per hour. Because of that immense speed, Einstein's theory of special relativity predicts that their onboard atomic clocks will tick just a little bit slower than the clocks on the ground. The difference is minuscule on a human scale. It adds up to about 7 microseconds, that's 7 millionths of a second, every single day. Okay, 7 microseconds. That sounds utterly insignificant, right? Who cares about 7 millionths of a second? But you have to remember, GPS lives and dies by nanoseconds. 7 microseconds is 7,000 nanoseconds. At the speed of light, a timing error of 7,000 nanoseconds translates to a positioning error of over 2.1 kilometers. That error would accumulate day after day. Just from this one relativistic effect, your GPS would become useless very, very quickly. But that's only half of Einstein's story. Because he wasn't done rewriting the laws of physics. 10 years later, in 1915, he published his masterpiece, The Theory of General Relativity. And this is where it gets even stranger, and even more important for GPS. General relativity is a theory of gravity. But it says gravity is not a force in the way we usually think of it. It's a consequence of mass and energy warping the fabric of spacetime. The famous analogy is a bowling ball on a trampoline. The heavy ball creates a deep well or curve in the fabric. A marble rolling nearby will have its path bent by that curve, making it look like it's being pulled toward the ball. Einstein's radical insight was that this warping doesn't just affect the path of objects in space, it affects the flow of time itself. The stronger the gravity, the deeper you are in a gravity well, the slower time ticks. Time in the penthouse of a skyscraper literally ticks faster than time in the basement. GPS satellites are way up high, 20,000 kilometers above the surface, where Earth's gravitational grip is significantly weaker than it is for us down here on the ground. They are much farther out of Earth's gravity well. So, according to general relativity, their clocks should tick faster than ours. And they do. This effect is much more pronounced than the one from special relativity. It causes the satellite clocks to run faster by about 45 microseconds every single day. So now we have a cosmic tug-of-war playing out in orbit. Special relativity, the theory of speed, says the satellite clocks should be 7 microseconds a day slower than us. General relativity, the theory of gravity, says they should be 45 microseconds a day faster. One theory slows time down, the other speeds it up. So which one wins? Which goes to stronger? As it turns out, they both win. You don't choose between them, you simply do the math. You have a 45 microsecond gain from gravity's effect, and you subtract the 7 microsecond lag from speed's effect. The net result is that the atomic clocks on board the GPS satellites, as viewed from our reference frame here on Earth, run faster than our ground-based clocks by about 38 microseconds every single day. 38 millionths of a second. Again, it sounds tiny. It sounds like a rounding error. But let's put this 38 microsecond problem in concrete terms. 38 microseconds is 38,000 nanoseconds. If the original GPS engineers had ignored relativity, if they had said, these are just weird theories, they won't matter in the real world, the system would have been a catastrophic failure. A timing error of 38,000 nanoseconds, when multiplied by the speed of light, equals a position error of about 11.4 kilometers. And that's the error that would accumulate in a single day. The error would start the moment the system was turned on. In 1 minute, your position would be off by about 8 meters. In an hour, it would be off by nearly half a kilometer. By the end of one day, your quiet suburban home would be plotted in the next town over. The entire multi-billion-dollar system, one of the cornerstones of modern civilization, would be completely, utterly useless. This is not a theoretical tweak. This is not a small correction. Einstein isn't just a portrait in a physics classroom. He is the silent, essential co-pilot on your daily commute. Without his equations describing the fundamental nature of spacetime, GPS would fail within minutes. So how do we fix it? How do we account for the fact that time itself literally runs at a different rate in orbit? You can't just change the laws of physics. So the engineers did something incredibly clever. They cheated. Before they even launched these multi-million-dollar satellites into space, they build the clocks to be wrong on purpose. Here on Earth, in the lab, they detune the frequency of the atomic clocks, setting them to run just a tiny bit slow. By how much? By that exact relativistic amount. They engineer them to lose exactly 38 microseconds per day. Then, when the satellite is launched into orbit and both special and general relativity kick in, the effects of spacetime warping speed the clock up by precisely the amount it was designed to be slow. The two effects cancel out. The result is a clock that, once in orbit, ticks at the perfect rate as seen from our perspective on the ground. It's one of the most incredible, and frankly gutsy, feats of predictive engineering in human history. They bet billions of dollars that Einstein's ghost was not only real, but that his equations were precise enough to build a global utility on top of. And the fine-tuning never stops. This initial detuning gets it almost perfect, but orbits aren't perfectly circular, and other small effects can creep in. So, a network of ground stations, with the master control station in Colorado, constantly monitors the satellites. They use lasers to verify their exact positions and check their clock signals. They then broadcast tiny clock corrections and updated orbital data, called ephemerides, up to the satellites, which then relay that information down to your phone as part of that hello signal. It's a constant, global conversation to keep time perfectly in sync. But Einstein's relativity, as mind-boggling as it is, isn't the only ghost in the machine. To get the pinpoint accuracy we need, the system has to account for several other weird and wonderful effects. For example, as we've been discussing all this, the Earth has been spinning. This creates something called the Sagnac effect. Imagine you're standing on the edge of a fast-moving merry-go-round. If you try to throw a ball to someone standing on the opposite edge, you can't throw it straight at them. Because the platform is rotating, you have to lead your target. Now imagine you have a ball-throwing machine at the center. It shoots one ball in the direction of rotation, and one ball against it. The ball traveling with the rotation will have a longer path to take to get to the edge than the ball traveling against it. It's the same for GPS signals. The Earth is a giant, rotating platform. From a satellite's point of view, the receiver in your phone is a moving target. Depending on the satellite's position and direction of orbit relative to the Earth's spin, the signal's path can be slightly lengthened or shortened. If we don't account for the Earth's spin, we get timing errors of tens of nanoseconds, which, as we now know, translates to tens of meters of position error. So, your phone's software quietly and constantly subtracts the planet's spin from the equation to keep you on the right path. And then there's the very definition of time itself. The satellites, once corrected for relativity, run on a perfectly steady, uninterrupted timescale called GPS time. It started at precisely midnight on January 6, 1980, and it has ticked forward with the relentless, even pace of atomic physics ever since. But the civil time on your wall, Coordinated Universal Time or UTC, is a bit messier. It's tied to the rotation of the Earth, which isn't perfectly stable. It wobbles. It slows down over time, thanks to the gravitational tug of the moon and Sunday. To keep our clocks aligned with the solar day, an international body occasionally adds a leap second to UTC. GPS time doesn't do leap seconds. It's a pure, uninterrupted count for the machines. As a result, the two time scales are drifting apart. As of today, GPS time is exactly 18 seconds ahead of UTC. This offset is broadcast by the satellites as part of their navigation message, so your phone can translate the perfect, steady time of the machines into the slightly messy, human-friendly time we use every day. So we arrive at the deepest, most profound paradox of the global positioning system. To find out precisely where you are in space, you must first solve for precisely when you are in time. Space dissolves into uselessness if time becomes fuzzy. And the more we look, the more we realize time is fuzzier and stranger than we ever imagined. Let's go back to general relativity for a moment. Time ticks faster in weaker gravity. This isn't just a theory for satellites in high orbit. It's happening to you, right now, as you sit there. Your head, being slightly farther from the massive center of the Earth than your feet are, is in an infinitesimally weaker gravitational field. Therefore, your head is aging infinitesimally faster than your feet. It's not a metaphor. It is a physical fact. If you lived your entire life in a mountain town, you would age measurably faster than an identical twin who lived their life at sea level. The effect is real, and has been measured. Now let's scale that down to a ridiculous degree. Raise your phone just 30 centimeters, about 1 foot. The change in the rate of time your phone experiences is minuscule, about 3 parts in 10 to the power of 17. A whisper of a whisper of a whisper. And yet, the latest generation of experimental atomic clocks, called optical clocks, which use lasers and different atoms like strontium or ytterbium, are now so ludicrously precise, accurate to 1 part in 10 to the 18, meaning they wouldn't lose a second in 15 billion years, that they can detect that difference. A single centimeter of altitude is now visible to time. This is the frontier. We are entering an age where time can be measured so well, it can be used as a sensor to map the world. In dense urban canyons, GPS signals bounce off buildings, creating echoes and ghosts that confuse your phone, a problem called multipath. But new global navigation systems, like Europe's Galileo, China's Beidou, and Russia's GLONASS, have come online. Your modern smartphone doesn't just listen to the American GPS satellites. It listens to all of them, sometimes tracking 60 or 70 satellites at once. More signals, and the ability to listen on multiple frequencies to correct for atmospheric delays, are all working together to slice through that urban haze, creating an ever-sharper picture of now. Ultimately, GPS forces us as a civilization to confront one of the most profound truths to emerge from physics. There is no single, universal now that everyone in the universe agrees on. That comfortable idea is a myth, a relic of a simpler, Newtonian view of the world. But what humanity has done with the GPS is create a practical now. We have bootstrapped our way to a shared timescale, GPS time, that is stable enough and precise enough for an entire planet to agree upon, so that we can all meet for coffee at the right place, at the right time. So, what does this all mean for us? On a deeply personal level, it means you are walking around with a pocket-sized time machine. A device that is constantly, silently, and perfectly reconciling the time-bending effects of immense speed and altered gravity. On a civilizational level, it's simply everything. The timestamping of financial transactions that prevents fraud, the phase synchronization of electrical power grids that prevents blackouts, the intricate logistics of global shipping, the timing of every packet of data on cellular networks, the entire invisible choreography of modern life rides on the steady, synchronized beat provided by these atomic clocks in the sky. If you were to pull that thread, our interconnected world wouldn't just fray. It would collapse. But the deepest implication is ontological. It's about the very nature of reality itself. We have this intuition that we just find places on a map. But that's not true. We construct them. We build our reality from a collective agreement among clocks, from a celestial choir of atoms humming a rhythm that lets us walk through space with a confidence that would have seemed like divine power to any human who lived more than a century ago. The blue dot on your phone is not just a location. It's the solution to an incredibly complex physics problem that was posed by Einstein 100 years ago. It's a testament to human ingenuity, a daily, silent validation of his genius, and a powerful reminder that the fundamental fabric of reality is far stranger, more flexible, and more beautiful than it ever appears. The next time you pull out your phone and see that dot snap into place, take a moment. You're not just looking at a map. You're witnessing a symphony of nanoseconds, a perfect harmony between atoms in the sky and the ghost of a genius in the machine, all working together across the void to tell you exactly where you are, in a universe where can never be separated from when. This journey through time and space is just one piece of the puzzle. To see how our perception of reality is being warped by new technologies, click the video on your screen right now. And a question for the comments: what's one concept in science that feels like magic to you? Let's talk about it. And if you want to keep exploring the hidden forces that shape our world, subscribe to the Science Audit, so you don't miss our next deep dive into the hidden science that runs the world.